Hey everybody, Dr. Retzik back with you here. This is our fifth video in Calc 4, and it's actually the second video on Section 14.3. So far in 14.3, we've introduced the notion of partial derivative. You guys know that the partial with respect to x is the slope of the surface in the x direction, and you know that the partial with respect to y is the slope of the surface in the y direction. And we'd like to do a couple more examples today and think about the difference between possessing partial derivatives and being genuinely differentiable. And those are actually two different things. But let's start off with a concrete example. This is something like a suggested problem you could see in the 14.3 exercises. So this is 14.3 continued. I'm going to do that in black. There we go. This is 14.3 continued. So this is more on partial derivatives. So sometimes when you're trying to find the slope of a surface in the x direction, the surface is given not explicitly as z equals stuff with x's and y's, but rather implicitly as just some big mess with x's, y's, and z's in it. And that's what this first example is about. So let's suppose we want to find dz dx at the point 1, 1, 1 on the surface. How about xy plus z cubed x take away 2yz equals 0. So this is what I mean by a surface being given implicitly. You see how we don't have anything nice here. We lack z equals stuff with x and y. We don't actually have a formula, z equals stuff with x and y. What we have instead is some equation with the x's, y's, and z's all tied up together. Now, it doesn't change the fact, though, that whatever that equation dictates, it's some kind of a surface. It's something, and the point 1, 1, 1 is definitely on there. I mean, look back at this formula here. You tell me. Is that true when x, y, and z are all 1? A quick calculation shows that it is. So this is a surface, and 1, 1, 1 is on that surface. And so you really could ask, well, what is dz dx? What is the slope in the x direction through that point? And we need to be able to do it even though we can't solve for z before taking a derivative. So this example illustrates the idea of implicit differentiation. You guys probably learned implicit differentiation in Calc AB. If not, we're about to do it right now. So we're going to take the derivative of both sides of the expression. So we're going to differentiate both sides of xy plus z cubed x take away 2yz equals 0 with respect to x. We're doing the x derivative. of both sides of that expression. Okay, so let's think this through. When you're doing a partial with respect to x, you treat the y's like numbers, and the x's are variables. Now, z is also a variable, because even if y is held fixed, if x is changing, z will change. So you can't pretend that the stuff with z's in it is constant. It's not. You change x, that'll change z. But we can at least pretend that all the y's are constant. Okay, so here we go. Let's differentiate both sides of this with respect to x. So this is a partial derivative with respect to x. Okay, focus on this first term. We're going to differentiate that with respect to x. Remember, y is constant and x is the variable. So the derivative of that first term is simply y. Okay, now focus on this next term. Z cubed x. Now this is the part where you have to be really vigilant. X is changing, which means z is changing. So this is a product of two things, both depending on x. So this is going to require product rule on those two terms. All right, so we have to do derivative of the first times the second plus first times derivative of the second. Let's talk about derivative of the first. If you want to do derivative of the first, well, the first is blah cubed. Therefore, its derivative is 3 blah squared d blah dx. So if we're doing derivative of the first, we got 3z squared dz dx all times the second plus first, which is z cubed, times derivative of the second with respect to x, which is 1. So in these brackets, you see a product rule on z cubed times x. Okay, there's a third term. Third term's right here. This one is sort of extra sneaky because you don't even see any x's. But again, when you're differentiating with respect to x, you're treating y as constant. Z, though, will change if x changes. Therefore, to differentiate that last term, you treat the 2 and the y as constants, and you differentiate z with respect to x. Now, on the other side of the equal sign, the derivative of 0 is 0, whether you're talking about with respect to x or with respect to y. Okay, so we have successfully differentiated both sides with respect to x. Now, zoom out for a sec. What were we even trying to do? We were attempting to find dz dx. Now, look at that left-hand side of the equal sign. Locate all the dz dx's you see. I see a dz dx right here. And I see a dz dx right here. Let's group those two terms together, factor out dz dx, and then put everything else on the right-hand side of the equal sign, leaving us with 3z squared take away 2y all times dz dx equals, and then move everything else to the other side. So what is that? Negative y take away z cubed, and that's it. Therefore, dz dx is equal to minus y minus z cubed all over 3z squared minus 2y. So the slope in the x direction on this surface at whatever point x, y, z is minus y minus z cubed all over 3z squared minus 2y. And in particular, if you wanted dz dx specifically at the point 1, 1, 1, you just stick 1, 1, 1 in for x, y, z, and you can see that the answer is 0 over 1, so 0. So this surface is actually flat as far as x is concerned at the point 1, 1, 1. Anyway, implicit differentiation can be a little bit tricky, and you just want to make sure you're treating the right things as variable and the right things as constant. And in this case, in this example, x was a variable, y was constant, and z was implicitly a variable depending on x. All right, so that example is just a little illustration of how to find dz dx, how to find the x partial when the surface is given to you implicitly rather than explicitly. Okay, let's return to an example from Monday and think about taking more partials. So I remember on Monday we had this. Return to f of xy equals, I think it was x cubed y squared plus x cos y. I think that was our function. That was one of the examples from Monday. Okay, and differentiating with respect to x is straightforward. So if you want df dx, we're starting to get good at this now. So what, 3x squared y squared plus cos y. And if you want df dy, then y is the variable and x is constant. So 2x cubed y, take away x sine y. Okay, great. So we take those first partials. Check this out. You could then take the y partial of the x partial if you felt like it. So now let's look at this expression here, and let's take its y partial. So we're going to get, what, 6x squared y, take away sine y. Likewise, we could have gone down to this line and taken the x partial of the y partial. So this is already the y partial. And then we could go on and take the x partial of that if we felt like it. And if we do that, we get 6x squared y, take away sine y. Oh, snap. These are equal. So this example makes it look like if you take the x partial and then take the y partial of that, it comes out the same as if you take the y partial and then take the x partial of that. Well, it turns out that this is true under some reasonable circumstances, but not always true. In fact, I think you're working on an example in weekly homework 1 where the mixed partials, that's what people call these, don't agree. But it's because the function's a little messed up near the point where you're computing those mixed partials. So in your book, in this section, you'll read something. It's often called Clairaut's theorem. I think your book calls it the mixed derivatives theorem. Anyway, it tells you the exact conditions under which you can expect the y partial of the x partial to agree with the x partial of the y partial. And by the way, notation for those second derivatives, this right here, this means, for notation-wise, notation, this means if you do d squared f dx dy, this means do the x partial of the y partial. So this is the x partial of the y partial, whereas this means do the y partial of the x partial. Now there's some unfortunate news regarding this notation. I feel bad every time I break this news to people. You remember the other symbols we used for partial derivatives? The ones with the little subscripts? That means y partial of x partial, and this means x partial of y partial. And it can be a little confusing because it looks sort of to be the reverse of the notation above, and that's really right, and it's the way of the world, and you just got to deal. So these two mean the same, and these two mean the same. Even though it looks like the order of x and y has been reversed. Anyway, it's just a notation thing, and you got to live with it, but just be aware. Lastly, we need to sort of return to the idea of differentiation. We're down with partials now, it seems. But that's not the same as being down with the idea of differentiation. That's just differentiation sort of one variable at a time. What does it mean for a surface to be differentiable? And what it means is a big analogy. So in the old days, differentiable meant when you draw the curve, the tangent line at a point is a very good approximation to the curve at that point. That's what it meant to be differentiable. If you zoomed way in, the tangent line and the curve would be nearly indistinguishable. Okay, you got to ramp that up by one dimension into the new days. Now in the new days, it's the x, y, z coordinate system. X out of the screen, y to the right, z pointing up. And it's not curves, it's surfaces. Maybe there's a mound like that in the surface. And it's not tangent lines anymore, but up one dimension, the analog of that green tangent line is that green tangent plane. So the definition of differentiability is not simply that the function has partial derivatives with respect to both x and y. It's more than that. The tangent plane to the surface needs to approximate the surface well. And you can imagine a contrived situation where there are perfectly nice partial derivatives, but the surface isn't even continuous. Do you have it in your mind's eye? Are you picturing the floating cross? That floating cross example is a nice example where the partials exist in the x and y directions, but the surface is not even continuous, let alone differentiable. The tangent plane for that surface doesn't approximate the surface well at all near that crisscross. So beware, It is not enough simply to possess partials to be considered differentiable. Differentiability is more than that. Now, you'll read some theorems at the end of this section. If you have partials and the partials are themselves continuous in an entire open neighborhood of the point at which you took the partials, then the function really is differentiable. But for now, just be aware of the difference and picture that floating cross example. Partials existing does not imply differentiability. All right, that's it for 14.3. You guys should read and you're good to go on any of the weekly homework and any of the suggested problems all the way up through Tuesday now. All right, I'll talk to you soon. Bye.